Welcome to the 49th lecture of surface engineering. We have had numerous discussions on various processes leading to change in surface microstructure or composition. In most of the cases, when you change the composition, you also end up creating new phase aggregates. Obviously, the microstructure changes. But we have seen also processes, for example, where we collided the surface with high energy spherical objects and created residual compressive stress without changing composition. Now, today we are going to discuss a very unique process where we are going to change primarily the composition of the surface without having made any major change in the overall phase aggregate or the microstructure. So we retain exactly, if it's silicon, we retain silicon, or if it is some tool steel, we exactly have the same phase aggregate, same phase identity. But we do introduce a new set of ions or new set of species which go into the solution as solid solution and primarily as substitutional solid solution, and in the process change either mechanical properties, structural properties, or functional properties like conductivity. So the process is ion implantation, and as the name suggests, we are talking about implanting or introducing new species ions onto the substrate surface. So we, while we actually try to introduce new species, for example, the one here, we have to worry about the trajectory that the incoming ion takes while entering into the surface, the range, the projected range unto which it actually goes inside, and the straggle, the spread that it encounters during the process of entering into the surface. So either in most of the cases, I would say more often than not, the incoming species, the ion, will have a definite mass, carry a definite mass with it, and of course the size or the diameter slightly smaller than the corresponding atom, neutral atom. So it will find its way into the lattice, into the substrate, solid substrate. But within the first few layers, it definitely will encounter either a direct or a glancing incidence impact. So when such a collision takes place, either direct or at some angle, the incoming species gets ricocheted, deflected, and then after deflection, it will actually change its path and eventually will come to rest below a certain depth from the surface. So this is the usual process of so-called multiple collision leading to implantation. But in very rare cases where you have particularly a lattice where the interstitial void size is relatively large, and more importantly, there could be a certain channel which actually offers a certain tunnel or pathway for the ions to penetrate deeper inside, depending of course on the crystal lattice that we are dealing with. In such a case, the ion can actually penetrate much deeper before it actually encounters any collision. Now that kind of a process, which actually is called channeling or so-called ion channeling, is not exactly what is desired when we want to carry out ion implantation, because the primary objective is to change the surface composition. So as the ion moves during its trajectory, as I said, there would be a typical depth unto which it will enter before it comes to rest after multiple collision events. And there could be a spread. So even if the angle of incidence is directly normal, still there'll be a spread, let's say up to this angle, there'll be a certain spread of the implanted species into different directions. And this typical range is the so-called lateral range of movement of the ions. On the other hand, there could be also a range in which an incident ion will actually undergo multiple collision and spread over a region, and that's typically called the delta RP or the straggle. We'll come to that in a minute. So the whole process essentially, the total ion implantation process we'll have certain elementary steps or the important steps. First is ionization of the species that we want to implant, then acceleration of the species. As we introduce the species into the chamber, we need to accelerate it to a very high velocity by application of very high electric field of the order of few keVs to MeVs. And then finally the injection or implantation onto the surface, and which can be typically a few tens to few hundreds of nanometers, but certainly not more than a micrometer, so way less than a micrometer. So these are the three important steps of ionization, acceleration, and injection or implantation. So what are the elements or what are the species that we want to implant? So if it's a semiconductor, then you would naturally think of elements either which basically belong to group 3 or group 2, if you want to create a p-type, or group 5 or 6 elements if you want to make an n-type semiconducting region. So accordingly you'll choose elements from phosphorus, arsenic, antimony, indium, or boron, or various other typical species. So, and by the by, the biggest and the most I would say widely applied application of ion implantation is in the semiconductor industry. So where that's purely because the precision and the accuracy with which you actually are able to carry out compositional change and hence change in electrical property. So we are talking about implantation dose, that is the concentration, typically about 10 raised to 11 to 10 raised to 18 species, number of species per centimeter square. So in a very small region, you actually can significantly alter the composition. So the energy with which the ions actually are accelerated would be anything like few hundred keVs. So up to about, you require the implanter to have a capacity of about 1 MeV maximum capacity, but typically you use about few tens of keVs to about few hundred keVs. As I was mentioning, the precision is extremely good, so you actually can create a region with the compositional reproducibility within less than 1%, maybe much less than 1%. So essentially we can dope anything from parts per billion to parts per million, and maybe a few fractions of atomic percentages. The beauty of the process is that this is not a thermally activated process. It's completely at room temperature. Whatever diffusion or mass transport takes place is essentially through ballistic diffusion, which means mechanically or species movement purely because of force applied from outside. So it's not thermally activated process, and the ion flux that is used to actually obtain such high dose would be something like 10 raised to 12 to 14 centimeters square per second. So you actually are injecting very high focus beam, high concentration of ions in a focus region. So in these conditions or this process, the two important factors is the dose, the number of atoms or ions per centimeter square, and the concentration, the total number of atoms per centimeter cube, the overall compositional index. So typically the dose would be the integration of the particular species, concentration of that over a period of time. So if this is the surface in which you are implanting and this is the distance, obviously the typical profile would look like this. So typically this is the depth you're talking about, but you integrate over the entire thickness of the material, and the total value that you integrate gives you the total dosage that you can achieve, which is at best would be somewhere in this range. So stepwise, as I said, you need to first carry out ionization. You need to accelerate the ions at applying very high voltage so that the ions actually carry sufficient kinetic energy and momentum to be implanted. Then you also need certain projection. You need a very well calculated change in trajectory, and then finally focus on to the specific spot where you want to implant. After implantation, there will be multiple collision events because of which the ions will progressively lose their kinetic energy and then eventually will come to a standstill. And so the loss of energy happens because of collisions, and some of these could be direct, but mostly these are glancing angle collisions. And then eventually the the ion basically acquires electrons and becomes a neutral atom and comes to a stop, comes to a rest. So these are the elementary steps involved in the overall process of implantation. There's one important thing that we actually must realize, that we are talking about essentially a process which is purely line of sight, which means if this is my substrate and if this is the ion beam if this is where the ion beam is implanted, so we are actually catering only to this region and not here or here. So purely the process is confined to the region which it is seeing, so it's a line of sight process. So we need a high voltage accelerator, because otherwise the ions will not acquire sufficient kinetic energy and momentum to be able to enter into the solid substrate. So it's like the area of the substrate may be small, but eventually compared to the size of an individual ion, it's almost infinite. But to be able to penetrate, you have metallic or ionic or partially ionic bond onto the surface, and you need to penetrate that. So that means you have to make your way through already a rigid body. So you require a lot of energy and momentum to carry with you. I already mentioned that we generally, for semiconductors, you go for elements which are either group 3 or group 5 or maybe group 2 or group 6 kind of elements. But the precursor is a gas, so that you can easily ionize. Say, for example, here the intended species is arsenic, here it's phosphorus, here it's boron. So you take various kinds of hydrides which are high vapor pressure, easily can be taken into vapor state, and then you ionize them by using certain electrical field. And you also need a mass spectrometer which actually will select and screen. So basically what species you want, you exactly select that one, and the remaining ones you can screen using a certain magnetic field. So you screen the ions of interest, and also this allows maintaining a very high purity. So this is another landmark thing. Apart from being a line of sight, this is also very important for us to remember, that this is extremely accurate and precise. We also can maintain extremely high purity. So in fact, this is possibly the purest form of altering the surface composition. So we need, as I said, a high voltage accelerator, typically maximum about 1 million volt accelerator, but usually we apply anything like 300 to 500 kilovolts. We also need a scanning system which essentially will allow the beam to be deflected in the X or Y direction. And this deflection will make sure that you are essentially implanting precisely at this spot and certainly not anywhere here or here. So in order to maintain this very high precision, you probably will need certain deflection or adjustment of the path of flight, either along X direction or along Z direction. So you need deflectors to do that. We'll see that soon. So the overall implantation system will have certain essential components, as I was saying. So first, of course, is the ion source. So here is the ion source, and a few tens of kilovolts will allow this vapor, the gas, to be vaporized and then subsequently ionized. Then you extract the ions, and then you make it bend almost 90 degrees. You bend such a way so that the neutrals are not needed anymore. And when you accelerate, you actually accelerate and make them converge at a very small focal point. And that's exactly when you energize the maximum, you accelerate the most. So you apply higher voltage, higher negative voltage, so that you accelerate the ions, and then you have a focal plane, and from there you again converge, and during the path of convergence you actually also bend again. This bending is intended to only extract or collect the ions with which are cations, which carry certain electrical charge. So then only you can actually bend them or deviate from their usual path, and the neutrals will continue to go in this direction. So I don't want the neutrals. So these are used as a beam trap by which you can trap the neutrals, and the ions continue to move in another path. And then finally you focus onto the substrate. So this is your substrate in which you actually allow the implantation to happen. So before you actually, as I was saying, in terms of the precision, I can move the beam in two possible directions, either along y direction or along x direction, and that's how I can make it implant or fall exactly on the precise point where I want. So in terms of a silicon, now typically the depth, as I said, is a few tenths of a nanometer, maybe 100, 200 nanometer, but the spread on the surface will be very, very precise. So you're talking about submicron features, or feature length or width could be maybe 10 or 20 nanometer, and you can very well confine within those regions by use of these kind of deflectors. Another very important point is that the distribution of the species is Gaussian. So the peak concentration is not at the surface, but below the surface. So the implantation energy has to be calculated such a way that there are two aspects, that while implanting you also create defects. So you don't want defect density to cross a certain allowable limit. But on the other hand, you also, unless you have sufficient energy, you will not be able to penetrate up to a certain depth. So you have to find the right choice. And in most of the cases, the wafer or the metallic substrate or ceramic substrate on which you're implanting is not exactly 90 degree to the beam, but maybe a few degree inclined to the incoming beam from the normal incidence. This is just to make sure that there is no ion channeling. The ions don't move through and through. The ions immediately encounter certain barrier sitting at this very first surface or within the first few surfaces, and then encounter certain collision. And once a single collision happens, then there'll be multiple collision events, because it's just like the carom board. When you actually hit the striker, or a billiard board, when you hit the main billiard ball, then it hits and then ricochets into multiple collisions. So that kind of implantation process allows implantation of the species to be concentrated and to reach a maximum concentration, not at the surface but below the surface, somewhere here. So the design of the process has to be done properly, so that we know exactly what would be the concentration of the species below the surface. Now this is the typical straggle that I mentioned at the very beginning. So it's just like the root of a tree. We know very well that below the stem, the root does not necessarily follow the same vertical direction, but it spreads up to a certain distance. So if this is where the ion is entering, if the ions are entering from this spot, so there'll be a range up to which they'll spread out. And this happens purely because of these multiple collision events, or so-called cascading effect. And then the concentration of the ions will be confined typically in this region. So this is the delta Rp. This is the so-called delta Rp. And this is Rp. This is the projected range. Now, injection to collision leading to eventual coming to losing all the kinetic energy and coming to a standstill. So during the increasing process of increasingly higher amount of reduction of energy, this creates a complex distribution of ions. So most of these are not possible to be predicted. The depth, of course, one can predict depending upon the surface condition and the applied voltage or acceleration voltage. But exactly what would be the path taken by the ions, there are multiple modeling exercises available, reported in the literature, which deal with it, because that's very crucial. What is the lateral diffusion or lateral spread of the ions? Say, for example, if you are trying to create a certain change in electrical properties of the semiconductor, you cannot afford to make it spread too thin along the lateral direction. Then you change the, then there'll be leakage current and there'll be overall deterioration of the performance. So the implantation system we already have seen will have this anode which will create these ions. So this is the ionization chamber, and then this is the opening through which the ions enter or are extracted into the chamber, and then, as I said, they are bent almost 90 degree using a certain magnet that we have here, and then we accelerate them by several hundred keVs, and then we use this X and Y direction deflections or deflectors by electrostatic mechanism, and then allow them to get implanted. So in this, the number of ions that we eventually are collecting into the substrate surface can be predicted or calculated, or the so-called implanted dose can be calculated indirectly using the or measuring the beam current. And I already mentioned that there will be multiple implants. In fact, you can actually change the species that you're implanting. So it's not necessary that when you're implanting boron or phosphorus, it has to be always like that. If you change the source, then of course you can make a certain amount of changes in the composition. So that's called ion mixing. Actually, you can add multiple ions onto the same implanted region and then make an alloyed region. The lateral scattering effects, they are always smaller than the lateral diffusion. In other words, what one calculates either as thermally activated or ballistic diffusion wise, the distance to which the ions are supposed to spread would be slightly higher than the so-called scattering effects that you. So the straggle that we saw would be smaller than the lateral diffusion distance, maximum distance that one can see. Another very important thing is that when we implant species onto the substrate, there will be a huge amount of crystalline damages created, primarily the point defects. So implantation will definitely create very high concentration of point defects, vacancies, self-interstitials. Even in case of semiconducting materials or ionic materials, some Schottky or Frenkel disorders and so on. So first thing is that we don't want direct normal incidence, so we always allow a certain angle of incidence with respect to the normal incidence, so that there's multiple collision events, cascading events leading to higher concentration being confined to the surface, concentration of ions. But while we enforce that, we also encounter certain amount of defects created by this process of implantation. So obviously, if you have a billiard ball here, and if this billiard ball is hit by another ball of same size or bigger size, obviously this will get deflected. So when it gets deflected, it can leave behind a vacancy, and in the process it can also push it into a position which is not necessarily a typical lattice position, but can be a self-interstitial position. So as a result, these defects are created. There's no escape from that. So what does one do? If you create a large concentration of defects, then obviously in the subsequent use, there could be defect induced diffusion and change in properties. In the extreme case, if you have a lattice, let's say if I have a lattice where I have obviously a three-dimensional periodicity. Now, if the implantation events are so violent that this fellow goes here, that fellow goes there, and this goes here, and you have a vacancy here, you create a vacancy here. So in the process, in case of a typical crystalline lattice, you would expect atoms or ions at regular intervals, right? And that's the so-called long-range periodicity. But if this fellow is missing here and this fellow is displaced somewhere here, this is deflected somewhere here, then along a certain distance, maybe along x or y or along z, if you don't see atoms or ions at regular intervals, then you question whether you still have a species, whether you are still dealing with a crystalline mass at all. So in such a situation, you actually can convert a crystalline matrix into an amorphous matrix, a matrix which does not have long-range periodicity. Now, obviously, the depth you are talking about, depth of penetration is few tens, maybe 100 nanometer, 200 nanometer. So it's not the bulk that you are changing, but the surface. You can create so much damage that the surface can get completely amorphized or completely lose long-range periodicity. That's purely because of the defect density that you create in the process of implantation. So in order to anneal out those defects, many of these semiconducting devices, wafers, actually are subjected to certain post-implantation annealing, thermally activated annealing process, whereby the atoms will come back to their respective crystalline positions. That means you'll restore crystallinity, and that also will improve the conductivity and ensure structural stability in future. So the implanter actually will have certain configuration. This we have discussed, so nothing new about it. You have ion source, you have pump, you have the analyzing magnet, the spectrometer, then you select and then you implant onto the species after this course correction, path correction. And the neutral trap, I have already said, is to arrest the neutral ions. So typical sources, say for arsenic implantation, you'll use arsen. For phosphorus implantation, you'll use a phosphine. So these are hydride gases, diboron and so on. Energy, as I said, this is the maximum, the few levels of MEVs, but that's rarely used. X and Y deflections are needed. That's the more elaborate view of the overall implanter system. So ionization, extraction into the acceleration tube, beam deflection through this mass spectrometer magnet. One other thing I should mention is that the need of vacuum. You're talking about typically something like 10 raised to anywhere between 10 raised to 9 to 10 raised to 11 torr. So very high vacuum level. And that's needed because if you have certain concentration of gaseous species, the ions will collide with them and lose energy way before they are able to implant onto the surface. So that means you are actually wasting the acceleration that you are spending so much time and effort to create high velocity and momentum of the ions. So you need absolutely extremely high vacuum, extremely high vacuum. The target chamber obviously has to be at the highest level of vacuum, and before they enter, there is an isolation valve which makes sure that the region here is completely devoid of any undesirable gaseous atoms. So you need actually certain scanning over the surface, certain rastering over the surface, and there are different patterns possible which will allow you to raster and then integrate over a certain surface area. So typically this is the kind of time scale that per wafer that you implant, because too high an exposure will create not only very high damage but also can create local temperature rise. The typical beam current will be in this order, a few milliamperes, and from which one can calculate what's the concentration of ions onto the surface. This is the frequency at which you actually do the implantation and also surface integration. So what all we have discussed in this part of ion implantation. We'll follow up in the next lecture also certain other features. So this is a process which, compared to any other diffusion control process, is completely driven process without any help or influence of thermal effect. So this is purely ballistic diffusion that we are talking about. The components, as I said, would be an ionization chamber, extraction chamber, acceleration chamber, then deflector using magnetic field, very high power magnets. Then acceleration also will require certain beam trap, the neutral trap, and then you have X and Y deflectors, and finally high vacuum chamber where implantation is carried out. You also may need certain manipulation of the substrate, the wafer, or maybe a metallic system in X and Y directions to cover a wider area. The spot, the focus is very, very small, so that too, this being a highly line of sight process, one of the biggest limitations would be that in an implantation you cannot think of covering, leave alone meter by meter, but not even a centimeter by centimeter area. So essentially you make a very tiny little spot of implantation. You require very high voltage to accelerate and give sufficient kinetic energy. You need very high vacuum, because without which there will be a lot of species, gaseous species inside, and collision leading to deceleration of the ions. It's a line of sight process. We have seen that it actually implants only where it is seen, where it is focused. We need a mass spectrometer, because with the help of the strong magnets we actually can focus and extract or remove the undesirable elements. The atoms are bigger than ions, so obviously you would prefer to use an ion for implantation than an atom. Otherwise there will be more of damage at the surface than implantation. So we have possible applications for metallic systems, say for example tools or prosthetic implants or very specific surgical instruments. For example, a hard valve where you want certain anti-corrosive or biocompatible properties to be imparted within up to about a few tens of a nanometer, maybe 20 nanometer or less, and for an area which is very, very small, maybe a few micrometers in diameter or something. So those kind of sophisticated and very precise applications for which ion implantation is ideal. For semiconductor industry, all the devices and so on are routinely used for changing their chemistry and hence the conducting properties. So with this, we'll stop here now, and then we'll move on to the next part of ion implantation in the next lecture. Thank you.